Hello everyone, in this video, I will present our work, Resilient Navigation Among Dynamic Agents with Hierarchical Reinforcement Learning. My talk will follow this outline. Nowadays, with the continuous development of the robot industry in recent years, more and more robots appear in our lives, such as household cleaning robots and shopping mall robots. In addition, the 3D animation and VR markets require realistic navigation algorithms to make virtual human more vivid and lifelike. Safe and efficient navigation algorithms will play an important role in our lives. However, it is still a difficult problem to design a safe and effective navigation strategy without knowing the intentions of the surrounding agents. This problem is challenging for two reasons. The first is that the agent needs to face a high degree of environmental uncertainty because it cannot control other agents in the environment. The second is that the agent needs to face various scenarios, and the navigation algorithm needs to be resilient when transferring to unfamiliar scenarios. In recent years, reinforcement learning shows the level of human beings in Go and games. More and more researchers try to apply reinforcement learning to navigation. Reinforcement learning does not depend on real datasets. It can continuously obtain training data through the virtual environment. Moreover, the optimization goal of reinforcement learning is the cumulative environmental feedback signal, which means reinforcement learning concentrates on long-term interests. Navigation algorithms can be classified to conventional methods and learning-based methods. Conventional methods are designed elaborately, but researchers behave well in the specific application scene, while they rely on handcraft functions and cannot generalize well to various things. Imitation learning can learn real human behavior. However, the application of imitation learning is limited to scenarios similar to the collected data. Reinforcement learning does not rely on real datasets. It can continuously obtain training data and get feedback from the virtual environment. However, reinforcement learning faces a huge search space, so it is difficult to converge. And even for two similar tasks, the model needs to be trained from scratch, so it is difficult for the model to quickly adapt to the new environment. To address this, we propose to use hierarchical reinforcement learning to generate plausible and collision-free trajectories. The main contributions of our work include: first, we built an effective and novel HRL framework to get the agent to reach the destination efficiently. By using hierarchical reinforcement learning framework, the navigation task is decoupled into target driving and collision avoidance, so that a stable and robust model can be trained, which can quickly adapt to a new environment. Second, through comparisons with state-of-the-art RL-based methods, our model achieves superior performance, especially in various challenging resilient experiments. In this paper, we present a hierarchical reinforcement learning-based navigation algorithm. This figure shows the overview of our method. Our model takes inspiration from feudal reinforcement learning. There are two levels in our model, where high level and low level communicate via explicit calls. We use this two-level structure to decouple the navigation task into target, driving, and collision avoidance, leading to a fast and stable model to be trained. Both of high level and low level are constructed by deep learning model. They share the same neural network structure. Here we introduce the deep learning network. Every time step, we can get the recent obstacles trajectories from the environment. Then we transform these trajectories into the laser form. The left bottom figure shows the visualization of the laser from data, which is a 6 by 360 matrix. The dark color means the agent is close to the obstacle on this degree. We construct the neural network as the right figure shows. The input data includes two vectors, OZT and OPT. OZT are converted from obstacles history trajectories. OPT are converted from the prediction trajectories on history. After introducing the structured deep model supporting the high level and low level, let me introduce the specific design of high level and low level separately. First, we introduce the high level module. The high-level module is at a lower temporary resolution, which means it will give a high-level policy every C time steps. Here C is a hyperparameter. The high-level module is responsible for calculating balanced sub-goals and giving them to the low-level module. These sub-goals need to consider long-term benefits. As the figure shows, both high-level and low-level modules train their policies through reward signals already obtained from the environment. The responsibility for high-level module is giving a good sub-goal to low-level module, which can balance the need of the reaching final goal and keeping safety. In our model, we consider three factors in the high-level module. The first factor is unit goal, which represents the relative distance the agent moves per unit time. The second factor is extra path, which is the difference between the distance traveled and the displacement. The third factor is close dist, which is used to punish too close to an obstacle. The low-level module calculates primitive actions at a higher temporary resolution, which is two-dimensional velocity in navigation. Compared with the high-level module, the low-level module calculates the primitive motion with a higher temporary resolution, that is, the two-dimensional velocity in navigation. The low-level module actually interacts with the environment. The responsibility of the lower-level module is to safely navigate to the sub-goal calculated by the high-level module. If the agent collides with other obstacles, we will give a penalty or collision. If the agent is too close to other obstacles, we will penalize the uncomfortable distance. Otherwise, we will give rewards to encourage the agent to move towards the sub-goal. We designed the following three things to test our model. The red disk represents the agent, the blue disk represents the virtual human, and the star with the corresponding color represents the goal of the agent or virtual human. The picture on the left is the screen scenes, where an agent and a virtual person are randomly placed on a circle, and their target position is on the other side of the same circle. The picture in the middle is the circle crossing scene. Its design is similar to screens. The only difference is that circle crossing has 5 moving virtual humans. The right picture is the square scene. One agent and 5 virtual humans are randomly placed in a square. We designed two kinds of experiments. The first experiment compares the navigation capabilities of the model, where the training and test scenarios are the same. For example, train the model on squeeze with a diameter of 8 meters and test it on the same scene. The second experiment compares the resilience of the model from two aspects. We test the resilience of the model in terms of scene size and scene type changes. For example, train the model on square and test it on circle. We compared with state-of-the-art models, which are based on reinforcement learning. In order to fairly compare our model with other models, each test scenario will be repeatedly evaluated 100 times. We use several performance metrics, which are success rate, collision rate, average navigation time, and kinetic energy. As the table shows, our model has the highest success rate among three things. The navigation time of our model is the lowest in the squeeze and circle things. To give an example, here are some simulation results on the circle scene. We can find that our model uses the shortest time to reach the destination. For the resilience comparison on scene size as shown in the table, we can say that the volume-based models CADRL and SARL perform poorly on the scene squeeze and circle, with success rates of 0.03 and 0 respectively. Our model and Long's work use a policy-based approach. The policy-based approach uses a policy network to learn the relationship between environment, states, and actions. Therefore, even when encountering unfamiliar environment conditions, the policy network still knows the general direction of the action. As shown in the table, when the scene size increases, the success rates of Long et al. Are 0.76, 0.7, and 0.53 respectively. Our method maintains the highest success rate of 0.96, 0.95, and 0.92 respectively, which are significantly higher than the volume-based method. However, as the complexity of the scene increases, the method of Long et al. Will lead to a higher collision rate, while our method still maintains a very low collision rate. In the experiment to test the resilience on scene type, we train the model on the square scenes and then test the model on the circle scene and the square scene. The scene sizes for training and testing are the same. When faced with unfamiliar scenes, CADRL and SARL retain a certain amount of navigation capabilities. For example, the success rates of CADRL on circle and square are 0.65 and 0.67 respectively, but our model has a success rate of 0.99 and 0.92 on circle and square respectively. Its performance is highly superior to other models. In order to verify the effectiveness of our model, we will show 3 ablation experiments at different levels. First, we compare high-level modules. Next, we compare low-level modules. Finally, we compare the hierarchical structure and monolayer structure. To verify our high-level modules' effectiveness, we compare our 2 conventional methods using ORCA and linear interpolation to calculate destination for the low-level module. The low-level modules are the same for RL, ORCA, and linear, and we'll calculate 100 trajectories for each method. As shown in the table, in the unit goal and extra path indicators, our method shows comparable performance. In the indicator closest, our method performs significantly better than the other 2 models. For the low-level module, we use the policy-based approach. There are 2 policy exploration methods for policy-based approach. The representative algorithms are PPO and DDPG. We test PPO and DDPG respectively to select the appropriate exploration method. As shown in the figure, the deterministic policy has a higher success rate and faster convergence speed than the stochastic policy in the training process. Therefore, we chose to use DDPG for our low-level module. To verify the effectiveness of our hierarchical architecture, we compare our model with a monolayer RL model. The reward function and training configuration of monolayer reinforcement learning are the same as the low-level module of our model, except that the low-level module calculates velocity policy based on sub-goals, while the monolayer model is based on the final goal. We compare the 2 models in a concentric scenario. The test results are shown in the table. The success rate of our model is 0.99, which is much higher than the monolayer's 0.18. As shown in the simulation results, the policy of the monolayer model is aggressive, and the agent goes directly to the final goal. Although the agent tried to avoid nearby obstacles, the high density eventually led to collisions. Our policy avoids high-density crowded areas through high-level calculated sub-goals, and these sub-goals are represented by red stars. Thank you for listening, and please read our full paper if you are interested in the details of our study.